Go.
Hello, my dear students. I want to briefly demonstrate balancing equations as we enter into our study of reaction stoichiometry and give you a couple of examples directly from some of the homework about how you can make these calculations, these determinations, so that the two halves of the equation are balanced. We'll hardly ever go over 10, and I promise on the test you won't have to take your shoes and socks off. I'll keep all the numbers in our examples on the test to 10 and under, so you can count them on your fingers. You can have a calculator if you want, but you really don't need one. And there are some paths for you to follow and some instructional ideas. It's like solving a crossword puzzle. You get a little bit and that gives you a clue to the next one. You make mistakes and you have to go back and choose, instead of a different word like a crossword puzzle, a different coefficient for your different substances in your reaction. But let's just go ahead and work one and look at some of the things I'm looking for. In one of the previous videos we had this example because we wanted to use these different compounds and elements and molecular forms of hydrogen, so also its elemental form, to calculate atomic mass and molar mass for molar quantities of both pure elements and compounds. But here we're looking at a reaction where we dissolve iron into sulfuric acid, make a salt, iron sulfate, iron 3 sulfate, and a gas. Little bubbles of gas come out when you drop a piece or some iron into a solution of sulfuric acid, especially concentrated sulfuric acid. So, what I want to do is balance this equation. I know a few things, and that is, this is pure elemental iron, and in the end I'm going to need 2. And a good place to start, and I would do this in pencil if I didn't know the answer already, would just be to say I need 2 irons. Okay? And I'm going to need 3 sulfates. Because look, for every 2 irons there's 3 sulfates. This is the classic example of a +3 and a -2. So this is iron 3, and sulfate, as you can tell when you look it up on your chart of polyatomic ions, is always -2. And so this is something we find all the time. Aluminum is +3, so always look for a +3 and a -2 with aluminums. Another good example might be calcium phosphate, where calcium is always +2, but the phosphate is always -3. So you're going to need, in this case, 2 + 3 irons to balance the charge on the 3 - 2 sulfates. You have +6, -6, and the compound ends up neutral as it should be. Not every problem is going to be written and give you this. It might be a pure word problem where they say elemental iron is added to concentrated sulfuric acid, and they don't give you any of these chemical formulas. You have to know the rules of naming to deduce a chemical formula. Okay? To give iron 3 sulfate plus molecular hydrogen. So, but I knew that I need 3 of these sulfates, so let me try 3 of those sulfuric acids. Now that would result in 1 of these, but look what I have. 6 hydrogen atoms. But it wouldn't be 6, would it? I have 3 sulfates here. So, this is going to need 2 irons. I'll need 3 of those sulfates, and that will give me 3 H2s. So my coefficients are 2, 3, 1, and 3. Okay, so I've balanced my equation. Let me show you a couple of other examples. And we'll come back to this particular reaction in the next video when I want to talk about what happens, how we use our stoichiometry when I say, okay, I don't have 2 moles of iron. What happens if I only have 1 mole of iron? Or what if I don't have stoichiometric amounts of my 2 reactants? Instead of a 2-to-3 ratio, what happens if I have a 3-to-4 ratio? What becomes limiting and how much product can I make? Those are the kind of questions that chemists ask every day and that we want to answer with the kind of problems we're working as we study stoichiometry. So let me work 2 more problems very quickly. In this particular one, this is one we're going to do in our 8-solution lab where we add iron chloride, a nice yellowish solution, to a solution of lead nitrate. We'll be working with lead. I want you to make sure that we work with small amounts. We're going to be working with dropper, sized amounts, drops of it, but once again, lead is extremely toxic, so we will wash our hands when we're done with this. But we're going to make iron nitrate and an insoluble precipitate, lead chloride, which is PbCl2, so it's lead 2 chloride. This is lead nitrate. It's lead 2 nitrate. So we didn't have any change in oxidation states. This is iron 3 chloride. There is a iron 2 chloride, which is FeCl2, of course. But so we have iron plus 3 and lead plus 2. So, we're going to have that same 2-to-3 probable ratio. So I'm going to take 3 of the plus 2s and 2 of the plus 3s and see what I turn out. Well, I had 2 irons here, so let me put 2 irons there. And each one of those has 3 nitrates. Each one of these had 2 nitrates, but there were 3 total. And now I'm going to have 3 leads and 6 chlorides, because it's PbCl2, so that would be 6 chloride ions total. And over here, each compound of the iron 3 chloride had 3 chlorides, but I had 2 of them. So all my atoms add up. Remember, I'm following, certain laws, and matter can either be created or destroyed. And this equation, this plus this, we use, instead of an equal sign, an arrow in chemistry, but it's like a mathematical equation. The 2 sides have to balance. Yes, we're, rearranging things, but in the end, we can either, create or destroy atoms until we get to the chapter on, nuclear chemistry at least. And when we do these reactions, the number of atoms on each side has to be equal. The mass of the reactants has to equal the mass of the products. So, we'll see that in some of the problems we're going to work. Here's another one. Ammonia plus oxygen produces NO plus H2O. This one, when I look at one like this and try to work it, I know, I have 3 hydrogens here, and I'm only going to have even numbers over here, so I'm inclined to say, well, let's try and find, 3 here and 2 here. Maybe 6 or 12 would be a common denominator. And when you try 6 and put a 3 here, it doesn't work out. So I'm going to start with a 6 there. So I have a total of 12 hydrogens and 6 oxygens here, but I have some more oxygens over here. So I'll worry about those in a minute. Let me deal with my hydrogens first. I tried it with 3, it didn't work. So now I have 6 hydrogens, 6 waters, and that gives me 12 hydrogen atoms. To get 12 hydrogen atoms, I would need 4 ammonia molecules. NH3 is the gas, ammonia. And now I have 12, and I had 4 of these ammonias, so I'm going to do 4 NOs over here, and nitrogen monoxide would be its official name, nitric oxide. This gives me 6 oxygens here, plus 4 oxygens in these compounds here. So, 6 and 4 is 10. Now this is molecular oxygen, or O2. So I need 10 oxygen atoms, but I will need 5 of these. That one was kind of hard, I admit it. But all you can do is follow the guidelines from the book and from the notes, and do your best. And if something doesn't work, try something different. Like I said, I saw here that I had 3 hydrogens here and 2 there. So I tried, that common, not denominator, but, when you multiply 2 times 3, you get 6. I tried a 3 here, but it didn't work out when I tried it. So I just went up and tried a 6, and that time, or this time, it worked. So balancing equations sometimes takes a little trial and error, but like I say, we need small whole number coefficients, and in this class, and for 99% of most chemical reactions anyway, we're not going to go into double digits. For chemical reactions to happen, molecules have to hit together and interact, and they have to do it in a certain geometry. And when you get 5, 6, 7, 8, 9, 10 of them going, now you can do it sequentially in steps, so you need to look at reaction mechanisms in a more advanced class, but you're not going to have a collision where these things are going to react to form new products, where huge numbers have to come together in a special spatial geometry. So, it is kind of cool. We can work with basically small whole number coefficients when we balance our chemical reactions. So like I say, next time, what would happen if I added more ammonia? If I had 5 moles of ammonia reacting with 5 moles of oxygen? But what would happen if I had 5 moles of ammonia and only 4 moles of oxygen? And how much product would I make? You may not care on a reaction like this, but if it's making an important product for some other use or for sale, then our ratios become more and more important to us. And when we want to have a good complete reaction without any waste, we also need to think about those considerations frequently in the lab. So this is a real-world skill that chemists have to master to be effective laboratory investigators. So we're going to move on to calculating different stoichiometric ratios in the next video, and then talk about a concept in the video after that called the limiting reagent. We'll also discuss briefly chemical yield, because we always want to know how much we're going to make. Or if I know how much I need to be able to calculate how much of the starting materials I need, how much I need to order, how much I need to mix together, what size reaction vessel I'm going to use, whether it's a pilot plant in a lab with tens of liters or a pilot plant in the plant with hundreds to thousands of liters, to, I told you when I was the Yale Celanese Biotechnology Fellow many, many years ago, there's a plant in Texas that produces 1 million gallons of acetic acid a day. I don't even know where you would put 1 million gallons, but you put it in tank cars and you ship it north. But my point is that when you're talking those kinds of quantities and you aren't efficiently following your stoichiometric ratios, you're just mixing stuff together and hoping you get enough product, then you're costing real money and wasting real resources when you do that. So balancing equations is a real-world, real-life skill that chemists need to master, and we will go on to look at this topic in a little more detail with some practical applications in the next video. Until then, stay safe.